week 4, and we are moving to our second type of machine learning algorithm, that is for decision tree. For this lecture, we have 3 objectives. The first, after the lecture, you will need to be able to explain how decision tree works in general, especially how to do the prediction and training for a decision tree. Second, you will need to be able to write pseudocode for classic decision tree algorithms. There are 3 of them: ID3, C4.5, and CART. Next one is optional. We possibly don't have time for it. That is, you will need to be able to explain pre-pruning and post-pruning methods for addressing overfitting issues in decision trees. In the previous topic for linear models, we talked about the use of regularization to address overfitting in decision tree. We have another common method, that is pruning. Let's first take a look at the basics of decision tree, what it looks like, and what we can use it for. From its name, we can see that we have 2 keywords, decision and tree. Decision here means that we try to use it to mimic or reproduce one way that a human being will make decisions. Second one major product or major tool that we use in this process that has a tree-like structure. So here I can give you a very simple example. Let's say that in engineering, if we want to decide whether we're going to go to the field to do a field testing, here we need to make a series of decisions, right, before we can finally tell we're going to do it or not. So we're going to do it or not. That means this is a binary classification problem. We only have 2 options: do it or not. In order to reach that final binary classification, let's say that we may need to take a look at several different things or attributes, features. First, we need to take a look outside to see what's going on outside, the weather, right? If it's snowing, no, we will not do it, right? We reach the conclusion. If it is raining, we don't do it. If it is cloudy, oh, yeah, we will consider that. If it is sunny, we will consider that, right? Then for cloudy and sunny, for the other 2, snowing and raining, we've already finished the classification task. We don't do it. And for sunny and cloudy, we need to keep going. So that's the first level of nodes in the tree. And of course, we have something called a root node. That's everything from the beginning. Next, for cloudy and sunny, we need to make some other assessment for some other attributes. For example, we want to take a look whether the equipment in our lab is ready or not. Ready? Keep going. Not? No, we won't do it today, right? Let's say that for the case when the equipment is ready, next is to, for example, talk to my team member to see if you guys want to do it or you guys are ready to do it today. If you say yes, keep doing that, you don't do that. And also maybe take a look at the coordinated with the people who in the field to see whether the site that we want to do the instrumentation is ready or not. Keep doing that. So that will create different levels of nodes for which of them we need to take a look at one condition to see whether, which condition we have. And that will determine whether we will reach a final conclusion, a decision, or in this case, it's a binary classification, or we will keep continuing. And for decision tree, of course, there are 2 things like what we did for any other supervised learning. That is, one is for training, the other one is for testing or prediction, right? Let's take a look how to do the training. And I think this is the more difficult part. If you know how to do the training, it would be fairly easy to figure out how to use a decision tree to do testing or prediction. And usually we draw the tree upside down. That means we start from the root node from the top. This is different from a natural tree. Natural tree, we have the root at the bottom. We use a rectangle to represent any non-leaf nodes. So for the trees, we have 2 types of nodes. One is the non-leaf nodes. The other one is the leaf node. And there's only one root node, and that's where everything begins. In the training process, what we do is that we feed all the samples, data points, into the root node, and we start from here. And at this node, any non-leaf node, we need to select an attribute, just like what we did in the example that I just gave. We need to assess one condition. What's the weather like outside? So select one attribute to split the data. Here, split data, that means originally we only have one data set, one training set for all, including all the samples. But after the samples is fed into this root node, we need to select one attribute. And for one attribute, we know that different samples may have different attribute values. For the weather conditions, some have an attribute value of sunny, some have snowing or raining. And the different attribute values will help us split the sample, the original data set, into several sub-data sets. And the number of subsets is determined by the number of attribute values that we have. In this case, let's make a simple example. Let's say that we only have two attributes. That means we will need to split the data set into two subsets. So let's draw something like this. And the two subsets will be fed into the nodes on the next layer. Or in some cases, we call the nodes on the previous layer called the father node, and the nodes on the next level, son nodes. But in this case, we only wanted to differentiate two things, the two types of nodes. One is the non-leaf node, the other one is the leaf node. In this case, let's assume that both nodes that we just got on the level right next to the root node are non-leaf nodes. These non-leaf nodes between the root node and all the leaf nodes, they are also called inner node. And again, this one is associated with attribute value 1, and this one is the same attribute. But for each attribute, we know that we have different attribute values. And also, they're associated with the subset, because we just split data, subset 2, and of course, this is subset 1. Next, we will take a look at the two son nodes or inner nodes that we just generated, and do the same thing. For example, for inner node 1, the one on the left, we want to take a look, we want to split data set again, the subset 1 again, further into another two subsets, or maybe more than two, depending on how many attributes we have, so attribute values we have. And for this one, we will need to select another attribute. And for this attribute, it has one requirement. That is, it needs to be an unused one on the same path. So on the path means that we go all the way from the beginning, the root node, and following away, reach the current node. And in that process, we may have passed through several nodes. And for each node, we know that we need to select an attribute value. So if the one attribute value has been used in the previous node on the same path, then we cannot use it again. That's the requirement. We select this one again to split data. Let's say in this case, we reached the leaf node. So leaf node here, we use an oval to represent it. And for leaf node is different from any non-leaf nodes in that they can tell us a decision, either for a classification or regression thing. In this case, let's say that give us a label 1. And for the other leaf node, give us label 2. So in this way, we can see that we just grew one subtree. It's called a subtree from here, from node to here. This part of the tree. And on the right side, the growth of the tree has not stopped because we haven't reached the leaf node yet. So we need to keep going. Here, we do the same thing. For this node, we also need to select an attribute for splitting. And we will get, let's say that this attribute has two attribute values. One will lead to a leaf node. The other one will just give us a inner node. So we use different attributes to represent it. For example, at the very beginning here, we choose an attribute. We use a star here. Now we get to the second attribute. We need to select another attribute here. Let's use another sign. Let's use an asterisk. And for this attribute, let's use a square. Finally, when we get to this node, we want to select another attribute again. Let's say it's attribute diamond. And for this one, we'll make a simple example. We say, oh, now we got three. This attribute has three attribute values. So we give us three different options. And all the options in this case lead to leaf nodes. So put in label 1, label 1, label 2, and label 3. So have three labels. That means it's the multi-class classification problem. And this is for the training process. You can see that the training process actually is a process in which we will split data sets from the root node based on different attributes that we select for the node that we generate layer by layer. Eventually, we will reach the leaf node, which corresponds to a target or label. Depending on the is by nature, the decision tree was proposed for a classification problem. You can see that because the output, there's infinite number of leaf nodes. So that is for classification. It's discrete. But we can also extend it to regression problems. This is for training and for testing or prediction. Let's see how to do it. That is, if you are given a decision tree and you have a sample, then you want to use the decision tree to feed the sample into the tree and tell, for example, for your classification problem, which category you have for that sample. For this one, let's do that. We only have, instead of have data sets for training, now we do it sample by sample. We have one new sample, and this sample has different attributes. Just like what we did. It has a star, it has asterisk, it has a square attribute, it has a diamond attributes. So in order to do that, we need to take a look at the value of each of them. Let's say that this one has an attribute value of 2. So you go from here, the root node, let me change the color a little bit. So we start from here. Now we are talking about testing. We have the value 2. So we go to the attribute value 2 to right. Here. Next, we assess the attribute value for this square. Let's say that square, we have a 2 as well. Then we will go to 2, attribute 2. Here's 1, 2. And finally, for the diamond one, we have an attribute value of 3. So we need to go from 1, 2, 3. Go from here. Eventually, we say that, oh, this one belongs to category 3 or has a label 3. That's how we use the decision tree to do a typical multi-class classification problem. Let's put down some notes just to summarize what we just did. So we can see that testing or prediction with a decision tree is very straightforward, while the training of a tree will involve a process of splitting T has two T's here, right? Splitting the training data set gradually, layer by layer, node by node. And if you observe this process again and think about it, you will find that actually we have some key questions in this process that will determine how we're gonna do the training. So we have two key questions. especially for the training process or for the tree growth process. The first question that we can get is, when can we tell a leaf node is reached? Right? We did not explain that, but this is kind of critical. For this question, I will offer 3 criteria, so you know that when we should stop growing the tree. The second question that you may get is how to select the attribute to split the data. We know that for every node, we need to determine which attribute that we will use for data splitting. So the selection of the attributes will determine what the tree looks like and how the data will be split. Here we need to make a decision for attribute selection at every node. And the answer to this question will lead to different decision tree algorithms. And that's something that we will be discussing after we finish introducing the 3 criteria. Here DT is short for decision tree. Let's take a look at the 3 leaf node criteria. The first criterion is that we need to stop, or we can determine that we reach a leaf node when all samples at the node belong to one category. In other words, data cannot be further classified. One category, that means there's only one class, so we cannot do classification anymore. Second criterion, we need to stop when all, so with this one, you will see that actually we have 2 conditions. When all attributes have been used in the previous node or nodes of the same path. Or, so this is one condition, or the samples have the same attribute value. That means that belongs to only one node. So it does not make any sense to create a second level node because there's only one on the next level. In other words, data cannot be further split. Here's not classified. And the third criterion is that we need to stop when there are no samples at the node. In other words, there's no data to split or classify. And many textbooks will give you the 3 criteria, but without explaining why. What's the story behind the criteria? So just take a look at the content inside the parentheses so you know the reason why. And also, there could be one very confusing point here. We talk about 2 things here. Actually, you can see that one is splitting, the other one is classifying. They are different things. We have both of them here. So make sure you understand the difference between split and classify. So let me give information, but split here and classify here. Classify is what we want to do because for a classification problem, we want to find what categories we have and which category does each sample belong to. Split is a special thing that we do in the training process of decision tree. We need to keep splitting the data so that we can grow the tree by adding more layers of nodes into the tree. So for splitting, it is done according to an attribute. Depending on how many attribute values we have, then we need to split the data into how many data sets. And we need to generate subsets. And you will find that each subset, they may contain data or samples belonging to multiple different categories. It's possible. Sometimes belong to one category, sometimes belong to multiple categories. That means we split data, but we do not classify it. So if we classify, then we only have one category for one sample. And you can see that this process, this splitting thing occurs at every every non-leaf node. We do the splitting at any non-leaf node, including the root node, and inner nodes. Second one for classification, this one is special. It occurs at leaf node. And if we do the classification at leaf node, then all samples at the leaf node or one leaf node belong to one category. And this category gives out the label. Please be aware that this is what happens without any pruning. These are the 3 leaf node criteria. Next, let's take a look at the second thing, which is associated with the second question. That is how to select an attribute to split data. What is the criteria? That also tells how we will grow the tree. To do that, first, we need to set up a goal for growing the tree so we know that which is the correct direction. Here, I give out this directly. The general goal to grow a tree, here grow a tree means this is a training process, is to make the information contained. We know that data contains information. So the information contained in the data, your training data, pure. Here, pure means that the data information has less chaos, less uncertainty. So this is the general direction. We set up a goal. We need to go along that direction. But how to get that go along that direction, how to get the destination, we then can select different routes that will lead to different decision tree algorithms. In order to, because we mentioned a few things when we are talking about the general goal, we have something called how to make the purity of the information, how much chaos we have or the uncertainty, and all these things are associated with the information theory. And you can find some information in chapter 1 in the week 1 topic. Go to the math part if you want to get more information about the information theory. Here I will give out the thing that we will use. How to quantify information. We will use something called information entropy. You should have heard this word entropy before if you did anything relevant to, for example, chemistry, thermodynamics. So in information theory, people borrowed the concept from thermodynamics. And this one is a measure of chaos. And actually is the negative of information purity or certainty. It has the following equation. Let's say that we want to get information entropy for 1D. So we write it in this way. HD, that means the information entropy of data set D. It can be calculated using this function. It has a negative sign at the very beginning. Then we need to take a look at all the categories. Let's say that we have capital letter K category, so that the small letter k need to go from 1 to the capital letter K, and this is a summation for a product of pk, small letter k here, times log to the base of 2 of pk. Next, let me explain what's the meaning of this pk here. Let's take a look at a very simple example. Let's say we have one node here, and we have data set coming from the top, and we need to split it at this node. If we make a very general example, let's say that we will split data into capital letter V subsets. Then we will generate capital letter V nodes on the next level. So we have, for the first node, the data subset associated with it is D1. We will put a superscript here, 1. Second one node is associated with subset D superscript 2. And this will keep going here between, we have general one, D sub K, small letter K. And of course, the final one, the last node should be for D capital letter, small letter V. Let's use V, capital letter V. If we say that for the initial data set, it has 100 samples, then for D1, D2, D capital letter V. Let's say that the first one, let's make one example. First one have 5 samples, second one 20, third one 15, and this last one 10. We can calculate PK. We split the data into V subsets. For each subset, it's very possible that we still have different categories, right? So let's take a look at D. Here should be DV here. For DV, we take a look how many samples we have. Let's say that it has 2 categories. Category 1, 2, K, all the way capital letter K. It may not contain all the capital categories, but let's say that here we take a look at this one. Move it here. So inside it, we have different categories. Let's say we have 4 of them. 1, 2, 3, 4. Then if the total is 100, then the sum of them need to be 100. Let's say 20, 40, 50. So we need to have another 50 here. Let's do 65. So in this case, PK here, let's say it's P3, should be 65 divided by the total. That's how we get the PK. And because of that, we can get a P value for each of the categories inside here. So PK should be smaller than 1, smaller or equal than 1, and greater or equal than 0. Sorry about the confusion. Then for this information entropy, we will find that the lower the HD value, the purer the information that D contains. And of course, the less the uncertainty. Indeed, that's easy to understand. At the very beginning, we don't know the classification, so there's a lot of uncertainty. Then we figured out how to classify things, put them into different groups. We will have a better understanding of this data, so the uncertainty will become less and less. And what we are trying to do is trying to find the best way to reduce the uncertainty, or find a way that to reduce the uncertainty as quickly as possible, as more effectively as possible. And here for this D thing, because we do the data splitting, so the total data should be V from 1 to capital letter V. So we put all the subsets together, we will get the total set. That's kind of a general thing about how to measure the chaos, the purity, or the uncertainty. They're just different aspects of data. Second, let's take a look at the classic decision tree algorithms. The first one and the oldest one is called ID3. So this is one of the earliest decision tree algorithm. And in ID3, what we do is that we use or we select the attribute that can lead to the greatest information gain. We write it as gain DA. Here means that we are trying to select the feature to split the data set D based on the feature A. Just the attribute or the feature A. What do we select? We call it information gain because we will have the information for data before splitting and the information associated with the data after splitting. We can compare them. We will find that the information entropy values were different from these two. It will drop. So the amount that drop in that process actually would be the amount of information that we gain by splitting the data. So we take the entropy, the information out in that data splitting process. That's why we call it a gain. And this information gain has a function gain D. Again, this is the information gain that we get by splitting the data according to an attribute A, data D according to an attribute A, that equals to two things. That one is the information entropy of the data set D before splitting minus the information information entropy of the data that is split according to A. So that is the information entropy of the data after splitting. And if we explain a little bit, here's the information gain from data during the data splitting process. And HD, that is the entropy of D before splitting. And this one is the entropy of data split according to attribute A. And that will be equal to HD minus, because for the information entropy for the data of the data after splitting, you will find that now we have capital letter V subsets, and for each of them we can calculate a information entropy. That's what we did. Depending on how many categories of data we have in them, we need to calculate the pk and then put them. You use this equation to get HD for that subset. And the total information entropy of this V subsets need to be a sum for all the capital letter V subsets. It's a weighted sum, and the weights will be the number of samples we have for each subset. Here, we put this sign here. dV is like absolute value or norm. Here it means the number of the samples in that set divided by the total number of samples. This is the ratio, the weight, times the HD small letter v. That means that's the information entropy of that V, small letter v. And this is the ID3 algorithm. Can you guys understand it? Sorry about the confusion that I made here when we are talking about this. Again, we split it into V sets, but this HG thing needs to be calculated for each subset because it's based on K categories. Depending on for each of them, we have how many different classes of data in it. Then we calculate the ratio of each of them. We calculate the P, and then we can calculate the HD for each subset. But we split the data into V subsets. We want to calculate the information entropy of all of them, not just any of us, just any subset. So we need to do the sum, or weighted sum. And the weight here is the number of samples that each subset will get in that splitting process. That is ID3. Again, we want to select the attribute that will help us get the highest information gain value here. And that attribute will be the attribute that we select at that node for splitting the data. That is ID3. Next, let's take a look at another popular algorithm called C4.5. Why do we need to develop another algorithm when we have ID3? Here's one major reason is that ID3 tends to select attributes that lead to more subsets. That is controlled by the information that the criteria, that's the information gain equation that we use in ID3. So the example is here. For example, we have one class of students. We use the ID3 to generate a tree. What's going to happen is that it will look into how many different attributes we have. For example, the first attribute that it will get something like age, like gender, like height, weight, right? And there's one attribute called your ID. Every student has a student ID. And then what this ID3 will do is that it will always select ID, because for ID, every student has a different ID number, right? Have a different attribute value. So if we have 50 students in this class, then it will generate 50 classes. But we know that that does not make sense, right? We don't want a classification model like that. And the reason behind this, we can explain it. That if you take a look at this information entropy equation, you will find that it has a function like this, from 0 to 1. So you can see that the value of this entropy will be lower when we get to two ends of it. Let's say this is pk. So when pk is really small, close to 0, or very large, when it's close to 1, then the information entropy value will be very small. And we want to get the highest drop. So we want to make sure that the information entropy of the subsets will be very small. In that case, we want to get more subsets, because when we get more subsets, each subset will have less samples. So in that case, we will turn inclined to get the lower information entropy values. And to solve this issue, C 4.5 uses a modified version of it called information gain ratio. So it's not information gain anymore. And this parameter is written as gain underscore ratio dA to replace information gain. The information gain ratio is defined as the information gain divided by a new parameter here. And this new parameter, we also propose an equation for it. It's like this. It's a summation for all the subsets from subset 1 to subset capital V. And this parameter is calculated based on the numbers of samples we have in different subsets. So D small letter v, that's the sample that we have in the V small letter v subset divided by the total number of samples in the data set before splitting times log to the base 2 of also dv divided by d. We do this because this parameter has a very unique function. That is, it will be lower when there are more offsets. So you can, subsets. So you can see that it has the same chain as this information gain ratio. So we put it into the denominator. So when the numerator and denominator change in the same way, it can offset the chain that we don't want for the information gain. That's how we address the issue. That is for C 4.5. And there's another algorithm called CART. This is actually what you can find in scikit-learn for decision tree. And this one uses another parameter to quantify how fast the uncertainty or the chaos in the information will drop, or how fast that we can gain information entropy from the data splitting process. The parameter is called a Gini index, and this Gini index is the weighted sum of another parameter called the Gini values of all subsets. Let's take a look at what is the Gini value. It has the following formulation. The original definition is that we want to get the products of this P possibility. That means the percentage of the samples in samples belonging to that category. And this original definition can be further formulated into one that we can easily use for calculation. And if you go to the textbook, you can find how this is done. So that's how you just need to calculate the pk, and then you calculate the Gini value for each subset. And the Gini index is a weighted sum of the Gini values of all the subsets. Just like what we just did for the gain ratio, we also need to get, here you can see that is also a weighted this is a weighted sum, and the weight is the number of samples we have in each subset. Subset from subset 1 to subset capital V, we have the weight, also the number of samples belonging to the small letter v category, subsets, divided by the total number of samples. That's the weight and the Gini value for the V subset, which is calculated using the equation above. And this is what we need to know for a decision tree.
I think I'm falling for you.